Hello. In my last video, I introduced the information. I explained how the information was a functional of the probability distribution and the various requirements that we have of this functional. I then used these ideas to derive an expression for the information in a uniform distribution, a distribution for an experiment with n possible and equally likely outcomes. I showed that this quantity was equal to minus k log n, as shown here. I further asserted that this is always the minimum amount of information that you can have about the outcome of an experiment with n possible outcomes, and that all non-uniform distributions with n possible outcomes would have information values that are higher than this. In this video, I want to derive an expression that gives me the amount of information in your non-uniform distribution, such as the one displayed graphically at the bottom of this slide. Our first step into doing this is going to be to introduce two further probability distributions. Throughout what follows, P will be the non-uniform probability distribution that we are interested in. Q will then be a probability distribution that we introduce so that the joint probability distribution, P times Q, is a uniform probability distribution over an extended sample space. Our reason for doing this is that if we can work out the number of elements in the extended sample space underlying the probability distribution P times Q, then we can work out the information content of P times Q as this probability distribution is uniform. In addition to these results, we are also going to use a result from statistics called the partition theorem. You can find more information on the partition theorem in this video, so please watch the video attached if you need a refresher. The reason the partition theorem is going to be so useful is that it is going to provide us a method for writing the elements of Q in terms of P. We will use this theorem to write that the element Qj of our probability distribution function Q as a sum over the elements of P. Inside the summation is going to be a product of the conditional probability that we get that particular element of Q, given that we obtained the ith element in the sample space P, multiplied by the absolute probability that we got the ith element in the sample space for P. As I discussed in some of my videos on probability, the product inside this summation is just another way of writing the probability of getting both the jth element in the sample space for Q and the ith element in the sample space for P. We proceed by noting that Wji here is a matrix of conditional probabilities, and that the summation here is just the product of a matrix and a vector. We can take this even further though, as we can recognize that in taking this product of a matrix and a vector, we are taking a linear combination of our set of conditional probability vectors as shown in the expression in the bottom right-hand corner of this slide. It is worth pausing for a moment here so as to spend some time taking this business of the linear combination in. In doing this, let's start by remembering what our first expression that we obtained using the partition theorem told us. We said that this expression allowed us to calculate the various elements of Q by taking the product of a matrix of conditional probabilities, Wji, and the vector of absolute probabilities for our probability distribution of interest, P. Let's consider an example of this. Let's suppose that there are two possible outcomes in the sample space for Q and three possible outcomes in the sample space for P. W is thus a 3 by 2 matrix as shown here. Now, if we take the product of this 3 by 2 matrix with this column vector, we get the following new column vector for Q. Notice this only has dimension 2 in accordance with our requirements. The first terms in the two sums shown here contain a factor of P1. The second term, meanwhile, contains a factor of P2, and the third term contains a factor of P3. We can thus exploit the properties of vectors to rewrite the column vector as shown here. This, though, is just a linear combination of the three columns of column vectors that together make up the matrix of weights W. In other words, we have arrived at the result that was shown on the previous slide. The probability distribution Q can be written as a linear combination of these W vectors as shown here. If we now insert the information that we have just arrived at in the expressions we started out from, we get the following. In doing this, note that we have just used what we have learnt in the previous slides to write the elements of Q in terms of P and this matrix of conditional probabilities W. Now notice that the Pi in this summation are just scalars. The Wi, meanwhile, are probability distributions. This realization allows us to rewrite the information as follows. In doing this, notice that all we have done here is once again exploit the fact that the information is additive. We are now in a position to finally derive our expression for the value of the information for a general probability distribution. Remember, I said that our strategy here was going to be to create a joint probability distribution, P times Q, that had a uniform distribution. Obviously, in doing so, I'm going to exploit all the results that I've just derived in the previous slides. Without further ado then, let's proceed by considering an example. I am going to consider the following non-uniform probability distribution. There are four possible outcomes to this experiment, which I am calling red, blue, green, and purple. Now notice that the probabilities of these four outcomes are not all the same, and that our probability distribution is thus non-uniform. Now it is relatively easy to construct this non-uniform distribution from a uniform one. We simply have to consider a sample space with 16 possible outcomes, 3 of which would be red, 4 green, 6 blue, and 3 purple. In other words, we could draw the sample space for this experiment using a Venn diagram like the one shown here. In this extended sample space, all the outcomes are equally likely, but the number of squares of a particular colour is in proportion to the probability of picking that colour. Let's now try to consider what the conditional probabilities, the vectors of w's in the expression shown here, are equal to. The key to doing this is remembering that these quantities are conditional probabilities. In our example, they are the conditional probabilities like the one described in the text at the top of this slide. These w vectors are the conditional probabilities of picking this particular green square given that you've picked a green square. Obviously, this is equal to 1 over 4. The key thing to realise is that the way we set up the sample space for our joint distribution P times Q, by making it such the number of events of type I was proportional to the probability for the ith element of P, made it such that these Wi vectors were all uniform probability distributions with Ni members, where Ni divided by N equals Pi, the probability for element I of the probability distribution P. Now, we know that the information content of a uniform distribution with n elements in its sample space is just minus k log n. We can therefore write the following expression. Here, n is the total number of events in the extended sample space, and ni is a number such that ni over n is equal to pi. To be totally transparent, for the example Venn diagram shown here, capital N is equal to 16, and the four ni values are 3, 4, 6, and 3 for red, green, blue, and purple respectively. Rearranging the result we've just arrived at, we can write the following. Notice that in doing this, I have taken the factor of k log n into the summation. This is why I have minus k pi log n on the right-hand side. Pi is a probability distribution, so if I sum all its elements, I get 1. I bring this term inside the sum, as I can then combine the first terms, the two terms shown here, using the law of logarithms to get the following. I then remember that I set ni such that ni over n is equal to pi, which allows me to rewrite ni over n as pi. I thus arrive at the following result for the information. The information contained in the probability distribution P, which could be uniform or non-uniform, is equal to k multiplied by the sum over I of pi log pi. Here, the summation runs over all the elements of the probability distribution. This is the key result that I wanted to arrive at in this video. It is the result that is important. The derivation is less critical in this module, but it is not difficult, so I presented it anyway. Please learn this result now, as we are going to use it extensively in the videos that follow. Thank you for your attention.